Hey everyone, thank you for joining us today. My name is Xinran and I'm a senior data engineer on the personalization data engineering team. Here's also my colleague Sundaram, and he's a senior software engineer on the real-time data infrastructure team. We're so excited to be here today and share with you how we backfill Flink pipelines using Iceberg Source at Netflix. This agenda for today, I'll first talk about Flink use cases at Netflix and why we need to backfill Flink applications. I'll also walk you through existing approaches along with these pros and cons. Then Senior will join us and discuss the technical aspects of designing Iceberg Source and how he came up with a solution to overcome event ordering challenges. At the end, I'll come back and share with you how to enable Iceberg backfill for your Flink application. Let's get started. First of all, I want to share with you how my team used Flink. I'm part of a personalization data engineering team, and my team builds and owns many different data systems that power data analytics and machine learning algorithms. One such system is the real-time merge impression app, which we usually call it RMI. One of the main use cases of RMI is to calculate take rate. Take rate is essentially the number of times a user watches a video divided by the number of times the video is shown to a user. In order to calculate take rate, RMI joins impression events and playback events in real time based on the set key to attribute play to impression. RMI data is critical input to personalization algorithms and also A/B experimentation analysis. Because of the large volume of impression data and playback data, RMI is one of the largest stateful Flink applications at Netflix. Just like any other types of software, Flink application can fail due to various reasons. For example, it can encounter error while reading from source or writing to sync. Dependent service fail can happen and lead into incorrect output. Upstream data changes can happen too, which breaks the assumption you make in your Flink logic. Oftentimes, the output of Flink applications serve as critical input to decision making for Netflix products. After failures, we need to backfill to mitigate downstream impacts. Here are a few possible types of backfilling you might need. For example, correcting wrong data that was previously produced by a Flink application, backfilling missing data for the period of times your Flink app was down, or using backfilling to bootstrap state in order to continuously consume live data from Kafka topics. The next question is, how do we backfill? The easiest way to backfill is simply rerunning the Flink job to reprocess source event from the problematic period. It's easy, just redeploy the job for a different timestamp. However, the biggest challenge here is Kafka topics come with limited retention, which means that when failures happen, you need to race with time to troubleshoot the failure, fix the problem, and replay events all before the source events expire. You might ask, why don't we just increase retention so we always have enough time? The biggest challenge is increasing Kafka retention is very expensive for huge datasets. Let's take Netflix for example. If we want to retain 30 days of data generated by our application, it would cost Netflix around 93 million a year. Not even mention that some applications will need more than 30 days of data. If Kafka retention cost is a problem, can we possibly store the Kafka event somewhere else at lower cost and backfill using that data? The answer is yes. Netflix Keystone platform provides a routing service that makes Kafka events available in other storage systems, such as Iceberg table on top of S3, so that they can be further processed by batch systems later. What is Iceberg? For those of you who are not familiar with Iceberg, it is an open source table format for huge analytic datasets. It offers many great features such as schema evolution, file pruning based on partition and column level statistics, time traveling, and version rollback. Last but not least, we compared the compression rate and storage cost for Iceberg table on top of Parquet file in S3. An Iceberg table offers 12 better compression rate and 98% less storage cost, which is great for ops. Let's take a look at how Kafka events look like in Iceberg table. On the left, we have a schematized stream of playback Kafka events, and there are the top-level attributes such as account ID, show ID, and view duration seconds. And when these events are routed to Iceberg table, All those attributes become top-level column in the Iceberg table. In addition to the original data contained in the Kafka events, Kafka metadata such as Kafka ingestion time are automatically attached to the table as well to be used later. So we have the Kafka events available in Iceberg table at lower cost. And can we backfill from Iceberg table? The answer is yes. Another backfill approach is to build and maintain a separate batch-based application, such as the Spark job, that is equivalent to the Flink application, but reads from Iceberg table instead. When failures happen, you just go to your Spark job and run your Spark job for the failed period. The biggest challenge with this approach is that the initial development of such Spark job can take days or weeks depending on the complexity of your logic, but also you need to do rounds and rounds of data validation to make sure the two parallel applications produce the same results. After the initial development for the future, you also need to continue to invest in engineering efforts to keep the Spark app up to date. As you can see, this batch-based backfilling approach isn't ideal either. To summarize, there are two common approaches for backfilling. One is batch-based backfill, which is about maintaining a separate app equivalent to Flink application. The advantage is the data retention is at low cost. However, engineers have to maintain two applications in parallel. Another approach is the real-time backfilling, which is about basically rerun the Flink application before Kafka source expire. The biggest advantage of this approach is that you can use exactly the same app for both production and backfilling, but the challenge here is increasing Kafka retention is very expensive. As you can see, neither approach here is ideal, which leads us to a question. Can we possibly combine the best things from both worlds?
And now, before you start to wonder what this magic solution is that can combine best of the both the worlds, that is precisely what the Iceberg Source Connector provides us. There are several nice properties about the Iceberg Source Connector. Firstly, it provides a generic solution for backfilling Flink applications without tying itself to the business logic. This makes it very easy to adopt it across a variety of Flink applications. Secondly, it requires very few code changes to add it to a given Flink application. Another excellent property about the Iceberg Source Connector is that since it's based on Flink's latest Flip27 source APIs, it can scale horizontally to the parallelism of the Flink application without causing any data skews on any one particular reader. This allows the developer to backfill the application quickly by throwing resources onto it so that he or she can jump onto live traffic quickly. And finally, we've evaluated the Iceberg Source Connector in production deployments, which gives us the confidence that this is indeed a viable strategy. Before we dive deep into the internals of the Iceberg source, let's try to understand the mechanics of it, of backfilling using it. As you can observe, when the application needs to process from the recent past, it reads this data from the Kafka cluster, which offers very low latency. On the other hand, when the application requires historically old data, which is not covered under Kafka's retention policy, it is read from the Iceberg table, which offers high throughput and thus allows one to complete the backfill as quickly as possible. Let's now look into the internals of the Iceberg source connector to understand how it satisfies some of our requirements. We'll also go over some of the fundamental challenges that we faced when building it. When we set out to build the Iceberg source connector, one of the first things that we looked into was check if there was already an existing integration with Iceberg that we could potentially leverage. We observed that in the OSS Iceberg community, there existed code to read from Iceberg table that works for both bounded use cases such as backfilling as well as for continuously streaming use cases. However, the existing OSS source still lacked certain properties that were critical to us. One, the source that existed did not support stateful Flink applications that expect events to be ingested in a given order that was very similar to Kafka, for example. Now, this was a critical requirement because the failure of this would result in backfilling producing incorrect results. Secondly, this was written using Flink's old source interfaces, which had its own set of limitations, making it hard to extend it, for example, to support something like data ordering. Because the existing integration did not satisfy all of our requirements, we set out on this journey to build an Iceberg source connector ourselves that can be primarily used for backfilling, but can also be extended in the future for other purposes, such as bootstrapping from historical state. We also were convinced that writing the connector on top of Flip27 would be the right path forward as we realized that coordination between the source connector and the reader was paramount to support something like ordering and alignment between sources. First, let's look at what building a source based on Flip27 API entails, and then let's try to connect the dots to the Iceberg source. Unlike Flink's old source APIs, where the developer was only expected to implement a simple source function that runs inside a task manager, the new source API involves implementing two separate components. One, a split enumerator that runs on the job manager responsible for two functions, discovering new splits and assigning them to readers as and when they request it. You might wonder what a split is, and the definition of it is very flexible. For example, in the case of Kafka, it can represent a Kafka partition. For something like the file source, for example, it represents a portion of the file. So, so that is the definition of a split. And we also have to implement a split reader as part of the Flip27 source that actually runs inside a task manager. And the responsibility of the split reader is that it should be capable of taking a split and emitting records by reading the split assigned to it. Fitting this into the Iceberg source connector, the split enumerator becomes responsible for populating splits from the table that contain the source Kafka data. The enumerator also is responsible for filtering the splits that just match the backfill period. When the reader requests for a split, the split enumerator assigns its splits based on the set of splits that have not been assigned in the past, and it's the responsibility of the reader now to emit records by reading the splits. In the Iceberg source context, you can think of a split as essentially a portion of the data file which is stored in Parquet or org formats usually. Okay, I know what you're all thinking. This is all a little too abstract, and it would be nice to look at this from the perspective of the code. So let's do that. Let's look at implementing the Iceberg split enumerator, which is the more interesting component in the Iceberg source. The reader, after all, just emits request by reading a split, and there are not very many challenges in a component. Flink has made it really simple to implement an enumerator. All we need to do is implement the split enumerator interface. And this interface, as you can see on the slide, has a number of methods to deal with various behaviors related to the enumerator. For the purposes of this discussion, let's restrict ourselves to just the first two methods. The start is a lifecycle method to do any state initialization, while handle split request, as the name suggests, is used to handle the case where a reader requests for a new split to be assigned to it. From the state perspective, we just need to keep track of the pending splits, and since this is bounded backfilling, we just have to initialize that once, and that can happen as part of the start method. The Iceberg client library, as you can see, provides really nice APIs to filter just the data belonging to the backfill period from the table and organize them into different splits. Now that we've initialized the set of splits that need to be read, when a reader requests for a split, if there is a pending split in the state, we can just return that. Otherwise, we can tell the reader that there is no more splits so that the reader can shut itself down at that point. Well, I know what you're all thinking. That should be fairly easy to productionize. What is he going to go over for the rest of this discussion? To answer that, I would say wait a bit. There are some challenges which we've not talked about yet. Let's go over them. One of the first challenges with the Iceberg source is that applications make assumptions around the ordering of data that's ingested into them. Because we want these applications to adopt backfill without any major changes to their business logic, it's important to respect these ordering guarantees. Failure to maintain them would result in application producing incorrect results, making the Iceberg source useless. We obviously don't want that. To understand this concretely, let's look at a real production Flink application. As you can see in the slide, this Flink application reads from the playback source. Playback source contains playback events collected from the user, and it essentially emits sessions from these playback source. The playback sessions are emitted into something like a Kafka sync. The most important operator of this application is the session initializer operator, and let's closely look into it to understand the kind of ordering assumptions it makes. The session initializer is just implemented as a key process function, keeping track of two states, the start and end of the playback session. If you look closely into the process element method, which gets invoked upon every new playback event belonging to a given user, you realize that what it does is very simple. It checks if the current event represents the start of the session. If so, it updates the start state. Similarly, it checks if the current event extends the current session. In that case, it extends the end state. And finally, it sets itself a timer to invoke itself uh, to to see if the session has not been updated in a bit of time, so that it can basically emit it to the sync. So the on timer method pretty much works like no as we had expected, which is that it checks if the session has not been updated in a given certain threshold. If so, it marks the session as complete and emits it to the output sync as well as clearing the state. Now, if you observe the code, you realize that it makes assumptions around how the data is ingested into the system. If, in light of the Iceberg source that we had built earlier, where splits are assigned in a random order, this would cause issues as the watermarks would progress incorrectly, resulting in invalid output. So even though the Iceberg source could compile and work with the existing business logic and the Flink application, it could lead to weird runtime behaviors, and that is bad. Now you think about this and you realize, okay, I know how to fix this problem. I'm just going to order the splits based on their ingestion timestamp and assign them to the readers in that order. Let's try to understand this visually. Let's say the enumerator requests for splits from the table, and let's say the table returns these 5 splits that belong to the backfill period. So the user is essentially trying, in this case, to backfill from minutes 0 to 15. And t equal to 5 to 10 essentially represents a split that contains data from minutes 5 to 10, as you can expect. Now, the enumerator, all it does is essentially orders these splits based on the ingestion timestamps and assigns them again based on the ingestion timestamp. So, in this case, when the readers request for splits, the enumerator assigns splits 0 to 5 to two readers so that they can be read. Once these splits are read and the reader lets the enumerator know that these splits have been complete read, then the enumerator can assign the next set of splits, which basically belong to the backfill period of 5 to 10 minutes. Okay, so this approach should solve the ordering problem and make the application produce the same output when using the Iceberg source. But there is one problem with this approach, and the problem is that the throughput is going to be limited to the number of splits that can be assigned in parallel, and this is going to be small. And the issue is that even if the developer wants to throw more resources onto backfill so that he or she can complete the backfill quickly, uh, because the number of parallel splits that can be assigned in parallel is limited, he or she is going to experience a very slow backfill, and that is not desirable. The easiest way to address a throughput problem is by relaxing the order constraint. So far, we've assigned splits strictly in their ingestion timestamp order. Although it provides correct results, Flink applications typically do not require such ordering guarantees and are usually written with some lateness in mind. Let's see how we can exploit that. Let's consider the previous example where the enumerator had to backfill data between minutes 0 and 15. So it had these 5 splits that it had to assign to readers. Let's assume that this application can tolerate a lateness of up to 10 minutes. Now, as part of this approach, we are introducing a new state called ingestion watermark that indicates timestamp up to which Kafka data has been fully processed. So initially, you can see that it is initialized to 0, indicating that Kafka data up to minutes 0 has been fully processed. Now, because the application can tolerate a lateness of up to 10 minutes, splits in the time window 0 to 5, as well as splits in the time window 5 to 10, can be read in parallel, as reading them will not violate the lateness constraint. However, split from time window 10 to 15 cannot be assigned till the ingestion watermark moves further, as reading it would violate the lateness constraint. Because we only have 3 parallel readers in this case, we can only assign the first 3 splits, even though the fourth split is also ready to be assigned. Now, once these 3 splits are completed and the reader lets the enumerator know of that, the enumerator can now move the watermark to 5, as all data till the 5th minute has been fully read. Because the ingestion watermark has moved to the 5th minute, this implies that data till 15th minute, 5 plus 10, can be read without violating any lateness constraint. Thus, splits 5 to 10 as well as split 10 to 15 will be assigned in parallel at this point. A nice property about this approach is that it solves the throughput problem of the previous approach while maintaining correctness for applications that can tolerate some lateness. You might wonder at this point, okay, this is all great, but does Kafka ordering even look like this? And do we not need to mimic that since that's the source we are trying to replace in the case of backfill? So let's first address the question of what type of ordering does Kafka actually provide. If you go through the Apache Kafka docs to answer this, you realize Kafka guarantees strict ordering per partition. What this means is that for partition 1, offset 5 will always be delivered before offset 6, and offset 6 will be delivered before offset 7, and so on. Across partitions, though, there are no ordering guarantees. Even though this is the ordering that Kafka provides, most Flink applications that deal with real-time analytics at Netflix use event-time semantics and are written with lateness in mind. For these applications, the rough ordering based on ingestion timestamp is more than good enough for both correctness as well as for performance considerations. Kafka ordering isn't required for these use cases. However, if we do want to guarantee Kafka ordering for other use cases, then what this implies is that on the right path, the Iceberg data will have to be partitioned along Kafka's partitioning scheme. This can lead to lots and lots of small files and can become exorbitantly expensive to store. Apart from being expensive, it will also hurt read performance due to the need to do a lot of IOs. Thus, use cases that require Kafka ordering are not under the purview of our Iceberg source connector. Interestingly, we don't have such use cases at Netflix. There is one more challenge with the Iceberg source, which is interesting to think about. Many Flink applications consume from multiple Kafka sources. Thus, these applications will need to read data from multiple Iceberg tables in the case of backfill. However, if one of the sources is significantly larger than the other, and if we were to backfill both the sources at the same rate, then there could be a huge watermark skew resulting in state size explosion. This manifests itself in the form of either slow checkpoints or checkpoint failures, making the backfill stack hard to operate. If it's hard to operate, developers will move to other backfilling means, such as using batch applications, which are easier to operate. Thus, this is something that also needs to be resolved to make backfilling using Iceberg Source a true success. Let's try to understand this with a concrete example. In this case, we are trying to backfill data between minutes 0 and 15 for two sources, 1 and 2. As you can observe, though, source 2 has 2x more data than source 1 and hence 2x more splits than source 1. Thus, source 1 will progress at approximately 2x the rate as source 2, causing watermark skews and thus state size explosion. So the question is, how can we solve this problem, as this is an important problem that needs to be resolved as well. One idea we can potentially explore is coordinating between the enumerators so that their ingestion watermarks advance similarly. Let's consider this idea. So one change we need to make to the previous approach of ingestion watermark is that we need to make this state global instead of it being local to every source enumerator. So what this would mean is that all the source enumerators will now have to coordinate with this global ingestion watermark tracker before they can assign new splits. Like in the previous example, let's assume that this application can tolerate a lateness of 10 minutes for both the sources. Thus, splits from 0 to 10th minute can be assigned in the case of both the enumerators, and you can see that happening in this slide. However, after source 1 splits are read fully, source 1 enumerator cannot assign more splits to its readers because source 2 is still lagging behind, and the global ingestion watermark is still stuck at 0. Thus, source 1's splits will have to wait for this to be updated before they can be further assigned. And this is what happens after the second set of splits are completed by source 2. In this case, you can see source 2 is trying to read splits up to minute 10, these three splits. So the global ingestion watermark is updated to 5 after these three splits are read by source 2. And this gives both the enumerators room to allocate splits up to the 15th minute. And this pretty much solves the problem of alignment between the sources. And you can see both the sources pretty much uh, updating their watermarks at a similar rate. To summarize, the Iceberg source involves implementing three different components. The split enumerator is responsible for discovering splits and assigning splits to the readers as and when they request them. It also lets the watermark tracker know about new splits that have been discovered so that the watermark tracker can keep track of the lowest ingestion watermark. The ingestion watermark tracker also lets the enumerator know in case of watermark updates so that the enumerator can go ahead and assign new splits based on these updates. Finally, the reader is responsible for taking a split that has been assigned to it and emitting records from the split.
Thank you, Syndrome. That was a great technical overview. For the next step, I'll show you how to enable Iceberg backfill for your Flink application. Let's use RMI for example. Here, you have the impression and playback real-time events in Kafka topics, and the RMI production job reads from those topics and writes to RMI output. At the same time, those real-time events are routed to Iceberg tables. And we set up a backfill stack that reads from those tables instead and read to the same output. Next, let's take a look at the code changes you needed to add Iceberg Source to your application. Here are some sample code from RMI app, and the impression source and playback source are already defined here. All you need to do is to add a few lines of code to add Iceberg Source. As you can see, the in-memory representation of the Iceberg source is consistent with the Kafka source, so you don't need to make any changes to the processing steps later. You also need to make a few changes to your configuration. Here, I define the backfill impression source to specify which Iceberg table to read from. I also added a dynamic source selector so I can easily switch between live source and backfill source later. Here is how RMI backfill job looks like on Netflix internal Flink UI. As you can see here, I can easily switch between Kafka Iceberg source through UI, and if I want to backfill, I just need to configure the start timestamp and end timestamp of the backfilling window. I also have the option to choose to read from one or more regions as well. When backfilling RMI data, we were able to process 24-hour data within 5 hours. We also did many rounds of data validation between production and backfill, and we found the backfill output matches up to 99.9% with production output. The minor description here has to do with the deduplication logic in RMI. In RMI, we merge multiple impression records together if they share the same key and take the minimum event timestamp. Therefore, depending on your backfill window, you might have a few impression records that have slightly different impression timestamp, but that minor description is very trivial to us. Here are some lessons we learned from backfilling RMI. The backfilling window depends on Flink logic. In RMI's case, it allows up to 1 hour of lateness, and also we hold impression and playback data in state for 6 hours. So in order to backfill 1 hour RMI data, we need to process 8 hours of data. If your Flink application have any event ordering requirement, you need to set max misalignment threshold. For RMI's case, we set this configuration to be 15 minutes so that the event will arrive no longer than 15 minutes late. And also, backfilling job needs tuning separately from production job because backfilling job will have source events arrive at a higher volume per second. Therefore, you might want to adjust your cluster setting so that you can achieve higher throughput and backfill more quickly. At the end, let's take a look at all the benefits that Iceberg Source has to offer. You can use the same Flink application both for production and backfilling, and you don't need to make any change to your business logic. It's very easy to set up, just add a few lines of code to add Iceberg Source to your application. Because Iceberg Source scales horizontally, you can backfill large historical data very quickly. Last one but not least is cost efficient. Returning 30 days of data previously cost about 93 million a year in Kafka, but in Iceberg, it will only cost about 2 million a year. At the end, I want to share a few items on the roadmap for Iceberg Source. For those applications that do not require sub-second latency, we want to provide support for continuous streaming Iceberg Source so that you can process incremental updates from Iceberg Source in real time in your Flink application. Secondly, we want to support hybrid streaming so you can bootstrap your application with historical data from Iceberg table and continue to consume live data. There are still some Flink applications that require strict Kafka ordering, such as CDC app, and we plan to support those use cases in the future as well. That's everything we want to cover for today. Thank you everyone for joining us, and please let us know if you have any questions.